pressure inside that space. Clear or not? Clear? So H2 is not ideal gas. How we know that? Because it has this temperature. Now for ideal gas doesn't have this temperature, inversion temperature, because for ideal gas, always the coefficient is equal to 0. Yes or no? Yeah, we don't need to think about temperature. We don't need to think about temperature, right? Why? Because simply, this is 0, and this is 0, so temperature is meaningless, right? Temperature is meaningless, so this stuff is always equal to 0 for ideal gas. Now the tricky thing is how to switch from this to there. I mean, how to check, how to get this equation. So we have to start from the state equation for a real gas, right? Then we just find this one. It will be a little bit complicated. And anyway, I'll explain maybe in next chapter, hopefully. Clear or not? Clear? You like it? Like this stuff? It's not complicated. It's a little bit complicated, but not hard. You just focus with me, right? You just focus with me. So we can control this. We can control this by what? Delta B, by expansion or compression, right? This can be controlled, right? Where we do the process at room temperature or at high temperature or at low temperature. And this is what? This is kind of constant. This is related to the type of the gas, the real gas, of course, right? We have to go to some textbook and we find the value, right? For most of real gases, this value is much bigger than room temperature, and this is like, make me relax. Why? I don't need to think. Maybe I'm here in this side. I'm in this side, but I have to check. This is expansion or compression, right? If I know my system, if I'm compressing the gas in the tire, right, and this gas is a real gas which has a temperature much higher, inversion temperature much higher than 300 Kelvin, then the valve temperature will increase, right? Right? But if I'm doing that in expansion, that will decrease. Any question? You like it? No, right? Okay. So now we have to prove this stuff again. I just wrote in red. I remember when I prepared the lecture a long time ago. So we have to prove it, but not mathematically. So this is the last thing I'm going to explain for today. So not mathematically. The thing I used before is mathematically. We start from dH is equal to dH over dt when pressure is constant, other stuff anyway. Or du, I'm sorry, du over dt when pressure is constant. But here, right now, we are using a more accurate way to prove this equation because mathematics is a pure thing. We don't know the path, and you know, in thermodynamics, everything is related to the path, right? How we are doing the process. So in reality, we don't need to use mathematics, but we use thermodynamics, right? We have a cycle, and in that cycle, we just go from A to B to C to A again, and then we can make this equation, or we can prove that this equation is right. Okay, but first stuff that we have to prove that this equation is right for ideal gas, and this is important. Ideal gas. Right now we have to distinguish between the real gas, ideal gas, and a real gas which behaves as ideal gas, right? Right? Okay, now here we come to here, CB, CV, and then A. Now in this case, guys, actually I didn't prepare a long time ago, but I will write down here. Now, for this case, we need to make a cycle. I just prepared it here. We need to make a cycle. And from that cycle, we see how the change in the energy. You know, in thermodynamics, everything about energy. So we deal with the stuff with the energy, right? So we have a system, and that system is a gas with a specific number of moles, and this gas is ideal gas. Then this gas will have pressure, volume, molar volume, and temperature, right? Now, we need to change this gas to a new state, right? A new state, right? Look, a new state. This is one state, this is another state in which B will be B plus dB, I mean pressure will change a little bit, and volume will be same, and this is constant volume, and temperature will be changed also, T plus dt. Right? D plus dt. Very good. Now tell me here, from this is one path. This is just path. From this path, what kind of thing we can find? Heat capacity at constant volume, right? Volume is constant. So here, guys, good thing that we can find CV, right? Right? This is good thing. But look, this can be done by using two different ways, or by using two different methods, I'm sorry. So let me take the space right now. This is the space. This is the temperature here, and this is the volume. Okay? Like molar volume. Now, initially this is the volume here at this temperature. Now our target to increase the temperature at constant volume. So what happened to the pressure? Pressure increase. Now, how I draw that usually, look. So we have this, and we have, you know, some fire here, right? Look, this is what? This is constant volume. If we increase the temperature, tell me the pressure. If we increase the temperature, then the pressure will increase, right? So this is what we have. So from here to here, then the bath is like this. This is the new temperature. But look, for this one, we can go indirectly. We can go indirectly and make a cycle, right? We make a cycle, right? So, okay, I will go first by this way. And I will use constant pressure. If I use constant pressure, then what I can find here, right? CV. Then gas, then pressure will be same, and I will change the volume. Or T, I'm sorry, plus dt. How we can do that, guys? What we need here? What does it mean? We are increasing the temperature, then the pressure will increase. Oh, I'm sorry, volume will increase. What happened? How would to do that? We just use this stuff? No, we use what? Piston. In the piston, we just make sure that external pressure is equal to the internal pressure, the gas pressure, and this is reversible, of course. What happened here? We just increase the temperature, then the volume will increase and pressure is constant. Clear? So slowly. Clear? So this is reversible and they are under equilibrium. Just keep that in your mind. So it will be like this. Right? So this is what? This is 1. Now this is 2. This is 1. This is 2, right? Now, what about 3? Look, what about 3? Tell me, 3 is what? 3 is what? A plus. A plus, not in this class, next semester class. If you take my mechanical metallurgy or mechanical properties, I'll give you A plus. Okay. Constant. Of course, everything is reversible here. We don't use rho. It will be what? Constant temperature. Then, constant temperature, what we write here? Constant temperature, what does it mean? Isothermal. Then, right? So it will be like this. Without rows. So this is what? This is a 3. Right? Now we come to 1. U1 is equal to what? Q plus W. And it's equal to what? W is what? Constant volume, 0. And Q is CV dt. Right? We just use this way. Right? Am I right? Confusing? What? No, right? This is U1. Now tell me, U2 is what? U2 is Q plus W, which is equal to what? Q CB dt, right? W is, pressure is constant, this is fine, right? Pressure is constant. So B, right? B, delta V, tell me, delta V is what? V2 minus V1. This is V1 and this is V2. It's equal to what? V plus dV minus V, right? So it will be equal to CB dt. Of course, minus here. Minus, right? Don't forget. This minus We always use it in the work, right? Okay, minus what? B dV, right? Now, U3 is what? 0, or delta U3 or U3 is 0, right? As I said before, right? Okay, I mean, we can use it this way. No worry, right? Now, tell me, the total energy of the system is conservative, right? The total energy means delta U1 will be equal to delta U2 plus delta U3, right? I mean, if we are going this way or this way, thermodynamic doesn't care about what? The back, right? So it just cares about the initial and the final state. So this way is U1 or delta U1. This way is delta U2 plus delta U3. But delta U3 is 0. So in here, delta U1 is equal to delta U2 plus delta U3. So molar, right? Now this is 0. This means CV dt is equal to CB dt minus B dV. Right? Okay, good. Now we are close to do that, right? This is ideal gas. This part is equal to what? Then this part will be equal to what? N. We don't use N here. Why? We are using this stuff, right? So it is equal to R over B. Right? If we just take dV over dt for ideal gas, it's equal to R over B, right? Because B is constant in this case. We don't need to take the differentiation of B, just temperature and volume. So we are trying to decrease the number of variables in here. So that's all. Now we come to here, it's equal to CB dt minus R, right? Minus what? Minus R. Of course, dt, right? Right? This is dV is equal to R over B, right? Right? So we need to dt here, right? Because I don't have dV over dt, I have just dV. Now dV over dt is R over B, then dV is what? R over B times dt. So I need dt here, of course. And now dt gone with each other, then finally we will have that CV is equal to CB minus T, minus R, sorry. Then CB is CV plus R, and it's all. Right? Clear?